versions of your function?
Yeah, I have been updating it.
Oh, you have been?
I believe so. I haven't checked that it really is reflecting the latest version I have.
No, I meant your homepage.
Yeah, I have been updating, but also you have to refresh your browser, right? Otherwise it will show you the old version. Okay, so let me try and remind ourselves a little bit where we are. So, you know, well, our goal is to show the existence of flips. We discussed that there's a reduction to PL flip. So in the situation of a PL flip, you have a PLT pair, X, S plus B. So S is an irreducible divisor that corresponds to the round down of S plus B. And this is a PLT pair. So S is the only non-Kawamata log terminal center of the picture. And then you have a projective morphism down to Z of relative Picard number 1. And the important thing is that minus, it's a small birational morphism, minus Kx plus S plus B is ample. And the goal is to show that the pluricanonical ring, so we want to show finite generation of this. And in order to show finite generation, we saw that it's enough to look at the image. So you look at the map of the restriction map given by a junction. And in order to show finite generation, it's actually enough to show that the image of this map is finitely generated. So you denote the image of this is denoted by sub S, the restricted algebra of Ks x plus S plus B. This is the restricted algebra. And it's enough, it suffices to show finite generation of the restricted algebra. So finite generation of the restricted algebra, we actually went through the proof, would imply finite generation of the original pluricanonical algebra, and then the flip is just given by proj of this. The reason is that the kernel of this map is essentially, after some truncation, is essentially a principal ideal, so there's only one other generator to worry about. Okay, so we want to show finite generation of this ring, and so in order to show finite generation of that ring, the goal is to show that this restricted algebra, Kx plus S plus B, is actually isomorphic to some algebra of the form Ks plus theta, where theta is a divisor between an effective divisor smaller than 0. And then, of course, this will be a KOT pair. So by induction of the dimension, this ring is finitely generated. So that's the goal here. So there's a small I here. This is true up to going to a higher model of S, but I'll try to explain that soon. So I have to show you how to construct theta, and I have to try and convince you that indeed, maybe not all the sections, so this is clearly a subring of R Ks plus B sub S. Maybe I don't know how to extend all of these sections, but I need to show you that I can extend these sections. So I need to convince you somehow that those sections can be extended. Now, of course, the tool that we are going to be using is some version of Kawamata-Vivek vanishing. And the version that we're using is called Nadeau vanishing. So remember what we proved last time. We proved the prodding proposition. Maybe I won't bother stating it for adjoint ideals are just stated for regular multiply ideals. So n is a Cartier divisor. And I'm assuming that n minus an effective Q divisor D is ample, where D is an effective Q Cartier divisor. Well, Q divisor, I'm thinking in this case on X smooth. Okay, then we have the higher cohomology groups of the ideal corresponding to this divisor D, twisted by oh well, okay, well, let me state it in the native vanishing version. These are equal to 0 for every I greater than 0. We stated a slightly fancier version last time where you, instead of just having a smooth variety, you had a log smooth pair and B was a reduced simple normal crossing divisor, and then we stated that you have vanishing of ideal of D with respect to this B, Kx plus n. Well, usually we write it Kx plus P plus n. But I think with what I do today, I'll probably just only need this version of vanishing. So let me write that version of vanishing. So why is that important? That's important. How does that relate to the previous statement? That's important because then we get that a surjective map from, in this case, okay, I can state it this way. So if S contained in X is a smooth divisor with no components in common with D, then H0 of I SD Kx plus S plus n surjects onto H0 I D restricted to S Ks plus n. Okay, so this is giving you a tool to extend certain sections from an adjoint linear series from a divisor to the ambient variety. And this divisor S, at the end of the day, is of course going to be that special divisor that we have in the PL flip. But now you see a problem. There is immediately something that's bothering you. We're not getting to extend all the sections, right? And we pretty much want to extend almost all the sections that vanish on BS minus theta we want to extend, where we haven't defined theta. And we're not getting to extend all of them, right? We have this pesky multiplier ideal sheaf. Okay, well, so the next lemma I'm going to give you tells you that sometimes you can ignore this term. So you can extend all the sections. Okay, so again, this seems to be a problem for our purposes, right? This ideal better correspond exactly to BS minus theta. Otherwise, we cannot extend the other sections. Okay, so here's the lemma. So sigma is a Cartier divisor. D and D prime are Q Cartier divisors, effective. I'm assuming that D is less or equal to sigma plus D prime, and that the multiplier ideal corresponding to, I think I don't need the fancy version, so let's just say D prime is equal to O of X. So this just means that the ideal is trivial. In other words, that's equivalent to saying that the pair XD prime has KLT singularities. Then the ideal of this Cartier divisor, so that's just OX minus sigma, is contained in the ideal of B. Not B, D prime. Right, so you have to think this D prime is probably happening on S, right? So the conclusion says that the section sigma that I'm looking at automatically belongs to this ideal. So if that's the section I'm trying to extend, no problem, it belongs to the ideal. So it gives me a way to check when certain sections belong to the ideal. So, okay, so what is this way? Let's look at it for a second. I mean, it's easier to prove than to really digest the statement. So what is this condition? Okay, well, okay, so that looks like a typo. So what do you think we should put here? You asked the right question. Right, that probably has to be the right thing. Okay, so what are we saying? So let's say that D prime was 0, right? Then sigma is greater or equal to D. So the ideal of sigma will be contained in the ideal of D. And since sigma is Cartier, the ideal of sigma is OX minus sigma. So in the case that D prime is 0, this is now a trivial statement to prove. So I probably wrote down the right statement. Now assume that, how big can I make D prime? So in essentially making D prime bigger, I'm making D smaller with respect to sigma and still keep this inclusion while I can increase it at most by a KLT pair. Okay? So it's sort of a reasonable statement. And just think about the case D prime equals 0, and then it's an obvious statement. And the proof isn't much harder. So let's do the proof. First of all, what is the ideal of D prime? Well, that's the trivial, right? That's O of X. But what does that tell us? Well, how do I compute this ideal? Remember, this was the push forward of OX prime, where X prime is a Röder solution, E minus the round down of the pullback of D prime. What is that E? That E is the gadget that appears when you compare KX prime plus, what notation do I want to put? Let's say gamma to be the pullback of KX plus E. So E is some kind of relative canonical divisor. Okay, so this push forward being equal to OX, this is just saying that E minus the round down of the pullback of D prime is greater or equal to 0, right? If you have a negative divisor here, it's going to force you to have a proper ideal, but it's a whole thing. Okay, so that's what that condition means. So let's see. I look at the round down of the pullback of D, then I claim that this is less or equal to the pullback of sigma plus the round down of the pullback of D prime. This is another trivial thing. I take this inequality and I pull it back, and then I take the round downs. This is a Cartier divisor, so the round down of a Cartier divisor is just itself. So that's why this comes out of the round down. Okay, so now I'm just going to take this inequality and that inequality and put them together and then push it forward. So what do I get? So this tells me that E minus the pullback of sigma minus the round down of I apologize. E minus the okay, let's do it this way. E minus the round down of the pullback of D. Yes, that's exactly what I want. Is greater or equal to E minus the pullback of sigma minus the round down of the pullback of D prime, which is greater or equal to minus the pullback of sigma. Okay, let's see if I did this right. So I start with this quantity. Why do I start with this quantity? Because the push forward is going to be the ideal of D. Okay? Now, the first inequality follows because from here. Pullback of D less or equal to pullback of sigma, pullback of D prime. I put a minus, so instead of less or equal, it's greater or equal to, okay, my handwriting is getting worse. Greater or equal to the pullback of sigma minus the pullback of D prime. So that's just from this inequality. And then from this inequality, E minus the pullback of D prime is greater or equal to 0, so I'm just left with minus the pullback of sigma. Okay, so now you take this and you push it forward, and this is what you get. The push forward of O of minus the pullback of sigma, Cartier divisor, so by the projection formula, is just OX minus sigma. And the push forward of this gadget, by definition, is the multiply ideal of D. So as probabilist, it's a completely trivial thing to prove. The hard thing is to know that this is a useful statement and to come up with the correct statement. And that's the curse of mathematics, right? A lot of the things you somehow, by playing around with it a lot, you come up with the right statement finally. And once the statement is the correct one, it's usually pretty easy to prove. Okay, so now, armed with these two results, this extension theorem and this lemma about multiply ideal sheaves, I'm going to prove the more impressive theorem that I stated last time. Okay, so remember the statement was like 4 lines, a bit of a mouthful. So x, s plus b plus d is some projective. It also works in the relative setting, but let me just state in the projective setting. Log smooth, so every divisor is smooth. The round down of b is 0, and they intersect transversely. And they have no common components, so s and b have no common components. And also s plus b and d have no common components. And I'm going to write delta as s plus b plus p, where p is some Neff divisor. And I'm going to assume that kx plus delta is Q-linear equivalent to D. So this is really, as I tried to tell you last time, it's really some condition about the stable base locus of kx plus delta, right? Because you can pick a divisor D in this linear series that is smooth. Well, maybe if you go to a resolution, you can make it smooth. That's not so much. The key thing that you should focusing is that it has no common components with s plus b, right? So the stable base locus of D does not contain any of the interesting geometry of this boundary divisor. Okay, and yes?
So in the application, you were saying, so D is given, and then you're going to try to find sigma and D prime. Is that how you apply it? This lemma, how do you?
No, actually, it's the other way around. Sigma is given. Sigma, when I write this down, is going to be the section I'm trying to extend, essentially. And then to show that you can extend it, you find some auxiliary divisor that makes all the vanishing work.
Or D and D. So sigma is given.
Right. So you need to find, in order to be able, essentially, this one is the one that I'll be able to extend, right? Because it vanishes along the ideal. In order to be able to extend that, well, okay, if my n is sufficiently ample, no problem. I just have vanishing. But if n isn't ample, then I need, and then it's not even Neff big, then I want to apply this kind of Kawamata-Vivek vanishing. So then I am looking for a divisor D with the property that it will kill this vanishing here, but the singularities of D are sort of bounded by the singularities of sigma.
Oh, I see. So you really extend
Yes, and then it will extend. So you have the section you want to extend. You want to find the divisor whose singularities on the restriction are pretty close to the section that you're trying to extend. Okay, so I'm only halfway through writing the statement, right? So now let's assume that some integral multiple k of p and k of b, these are integral divisors. So k clears the denominator of those divisors, some fixed from now on in positive integer k. And let's assume that h is sufficiently ample. Then, okay, here we go. For any section in k, ks plus b plus p restricted to s, and any section u or maybe general section, depending how I do the proof, but for some section in this very ample, sufficiently ample divisor restricted to s, and any integer, positive integer L, we have then L sigma plus U is in LK kx plus delta plus H sub S. So remember this symbol. This means the restricted linear series. This denotes the image of, you look at the linear series on the ambient variety, right? So what I'm saying is I have this section sigma. I cannot tell you yet that it extends. What I can say is I fix one very ample divisor. No matter how big a multiple I take of sigma, I can extend that section. And then the next theorem should somehow sort of divide this by L and take the limit, if that means anything. That doesn't actually mean anything stated that way, but morally speaking, that's what we'll be doing. Right? So instead of, and if you're familiar from a more analytic point of view, this is a typical thing that they do applying Anhern-Hsu's theorem. They extend this section, construct a metric on the ambient variety, and sort of take the limit of that metric. Take the limit of the m fruits of that metric to get a better metric. Okay, so in order to prove this theorem, all we need are those two propositions and a decent amount of work. The reason why I need a lot of work is because there are a lot of fractional divisors in this picture, but these proposition and the lemma, right? I mean, if you're talking about sections that you want to extend, they have to be cut here. So when I write this linear series here, I want to make it up of LK smaller adjoint bits, and I can't just divide it. I can't just use kx plus delta plus h over LK because that's a fractional divisor. It's not a Cartier divisor. So I'm going to have to sort of divide and take remainders. Okay. So Lm will be the division of m by k. Okay, so you take a number m and you divide it by k. This is the quotient that you get, and then there's a remainder. Rm will just be m minus Lm k. So I just did division of m by k. Okay, then I'm going to set, I want to define Pm will be Kp if Rm is 0, and it will be 0 if Rm is non-zero. Right, so you think of running m over the integers. And every time you pick a multiple of k, then Pm is Kp. And if it's not a multiple of k, you put Pm equals to 0. Now, Bm is another integral divisor. So how can I make an integral divisor out of MB? I can take the roundup of MB. But now, typically when you're doing an adjunction statement, you want B to be a reduced divisor. This has, as M gets big, this is a really big coefficient. So there's a way to view this as a reduced divisor. You now compare it with the roundup of M minus 1, B. So the difference along any coefficient between these two divisors could be 0, 1. So this is a reduced divisor, the kind of thing that you like to do adjunction with. dm is going to be the sum for I equals 1 to m of kx plus s plus pi plus bi. Yes, that looks good. So what am I thinking of this dm? Well, it's a bit like that d, right? So if you talk m kx plus delta, right, you'd expect, since delta, you'd expect to get m times kx, which is what we're getting. Now, what does delta look like? It's s, so m copies of s, which we have there. And then you'd expect to get about m copies of p. Well, m copies of p won't be an integral divisor. So maybe you'll get m divided by k copies of p, which is what we're arranging. And then you expect to get about mbi, right? About mb. But if I sum all of these, so what we'll be getting is, when I sum all of these, I'll be getting, I think, the roundup of bi. And whenever, of bm. And whenever m is divisible by k, that will actually be exactly the same as mb, as long as it's divisible by k. So I'm sort of doing an integral approximation of m times that q divisor that looks as much as possible as an adjoint, as a pair, as a log canonical pair, or even better, DLT pair. Okay, so for future purposes, I would like to record that this is the same as mkx plus s plus lmkp plus the roundup of mb. And I just discussed why these things appear. And let me assume...
Chris, I'm sorry.
Yes?
What you said that, but why is the reason you're persisting on have some integral thing?
Well, for example, if I want to apply my proposition, I need Cartier divisor.
N?
Yes.
Oh, N.
Yeah, so my n will be made up from this dm plus or minus a kx or something like that. So I need Cartier divisors in the picture, and I'm going to do a proof by induction, so every time I need to be adding something of the form kx plus a boundary, plus a reduced boundary. So that's what I have arranged with this trick. Okay, so I'm going to assume that dj plus h is very ample for 0 less or equal to j less or equal to k minus 1. You see, k is a fixed integer, so these dj's are finitely many fixed divisors. Since h is sufficiently ample, I can assume that this finite collection of fixed divisors is very ample. And I'm also going to assume that dk plus h, so the restricted linear series, is equal to the full linear series. Okay, just this one. Again, this is a fixed divisor. If h is sufficiently ample, you can kill higher cohomologies and get that this equality. And this looks awfully like the thing I'm trying to prove when L is equal to 1, right? So this is the basis of our induction. Basis of induction. Right? Because if you put L equals 1, it's the kind of thing that you're trying to prove. Okay, so let me write down my inductive statement. So claim, I know where sigma lies. Okay, for um in d rm plus h restricted to S, we have Lm sigma plus um in dm plus h sub S. So the thing at the top, so the case when k divides m, so i.e. m is equal to Lk, this is the statement of the theorem. Right, so the theorem, I'm only asking to be able to extend L sigma plus u, so I'm only looking at multiples of k times this quantity. Now, in my induction step, I'm going to prove something slightly harder, something slightly more general. I'm not just going to worry about multiples of this quantity. I'm going to look at some intermediate gadgets, right? So I'm going to look at, this comes from Lm, kx plus s, blah, blah, blah. This is the remainder, so I'm really looking at any multiple of kx plus delta appropriately adjusted. And every time that that m is divisible by k, I get the original statement. Okay, so we do induction on m. M equals k has already been done. That's my assumption, the basis of the induction. So now I need to choose, right? So I assume it's true in degree m, and I'm trying to prove it in degree m plus 1 or something like that. So what I'm going to do is I'm going to cook up, using my inductive hypothesis, I'm going to cook up an interesting other divisor that will allow me to apply the proposition and the lemma. Okay, so this is going to be a bit of a mess, unluckily. So here we go. For let's pick a small rational number, delta, between 0 and 1, very small rational number. Then I claim that d Rm minus 1 plus h plus delta Bm is ample. Okay, this should be a triviality. You see, the remainder is between 0 and k minus 1, so I know that d Rm minus 1 plus h is very ample by my assumption, and so I perturb it by a delta. So this, how small this delta depends on m, right? So given Bm, I can pick a delta. For any delta sufficiently small, this quantity is ample. So this depends on m. Now,
why is this? I'm sorry.
well, this is ample. Right, it's very ample. In fact, dj plus h is very ample with j in that range, and this is a remainder, so it is in the range. And this is just a perturbation of that, so it stays ample. Okay, so now I'm going to consider another small number, epsilon, and I'm going to let f is going to be 1 minus epsilon delta Bm plus Lm minus 1 times K epsilon D. So then x s plus f is log smooth, and the round down of f is 0, and s is not contained in the support of f. So let's check this. Okay, so what is f made of? F is made of b's and d's. Okay, but by assumption, s plus b plus d has simple normal crossing. It's a log smooth pair. So since Bm only lives on components of B, then by definition F also has simple normal crossing support. So this is clearly log smooth. You just think about it for a second. S is not contained in the support of F. It's clear. How about the round down being 0? Okay, so we discussed that Bm has coefficients 0, 1. So now the coefficients are strictly less than 1, so the round down is 0. And now, how about this guy? Well, Lm minus 1 times K could be pretty big. It's close to M. But I'm multiplying by epsilon. Again, depending on M, I can make this be arbitrarily small, so the round down is 0. So this epsilon also depends on M. Okay. So now, let's pick W in this very ample linear series, some general divisor. And let's let phi is going to be f restricted to s plus 1 minus epsilon w. Then it's clear that s phi is KOT. Why is that? Because f gives me a KOT divisor simply because it has simple normal crossing and the round down is 0. And now I'm adding something with coefficient, a smooth divisor that intersects this guy transversely and also has coefficient less than 1. So again, I get something that's KOT for trivial reason. Right? This linear series is very ample, so a general element in there is going to intersect everything. It's going to be smooth and intersect everything in the picture transversely, so this is clearly KOT. Okay. So, I mean, I'm just writing some trivialities. The only thing that's not clear is how did I know how to choose all of these divisors, right? And it's trial and error. You know, this is like a 5th generation statement, and every time you prove a statement like this, you get better at finding the right devices. Okay, so I've done nothing, but I'm sort of halfway through the proof. So I guess you should say this is a good time. You don't have to do anything, and it's going to work out for free. Okay, I have to use my inductive hypothesis at some point, so let's do it now. By induction, there exists a divisor G in dm minus 1 plus h, right? So I'm trying to extend this divisor in dm plus h. By induction, I know that I can do it at the previous level, such that the restriction to s, hopefully I can find the place in the note so I don't have to ad lib. G restricted to S is Lm minus 1 copies of sigma plus W. Let's see if that smells right. So in my, right? So my inductive hypothesis is just this with m equal, replacing m by m minus 1. So Lm minus 1 sigma is the right thing. Um is what? It's a section in drm plus h, and here we have it in drm minus 1 plus h. So that is indeed the inductive hypothesis. So I think this is the last auxiliary divisor that I have to define. So I'm going to set C is going to be, by definition, 1 minus epsilon G plus F. So this is less or equal to Lm minus 1 sigma plus phi, which is less or equal to Lm sigma plus Um plus phi. Okay, so let me check this. It's a triviality from what we've already shown, but you just have to chase them down. So phi is F plus 1 minus epsilon W, right? So this F is getting eaten up by the phi. There's something slightly wrong because I shouldn't be okay. This is the restriction to, oh gosh. Okay, so C restricted to S. Okay, so F restricted to S is contained in phi. So this part, when I restrict this to S, it's less or equal to that. How about G? What does G look like? G restricted to S is copies of sigma and a W. Okay, so phi has 1 minus epsilon W, so that's taken care of by the phi. And then I need this Lm minus 1 sigma. Oh, there's Lm minus 1 sigma. So this one is okay. And then, well, this is a bigger multiple. Well, Lm is greater or equal to Lm minus 1. It might be equal. So clearly this part is taken care of. I just added it in for good luck. And phi takes care of itself. Okay? So this inequality is just for why am I proving something like that?
There.
This one here, right? Yeah. That's where that inequality is coming. So that's telling me that if the multiply ideal is of this C restricted to S, then the section I want to extend is going to extend. Because I'm only off by something KLT. Okay, so that's good. Okay, but then if I'm going to be doing that, I also need to have some vanishing theorem. So I need to know that the numerics of C work out to give me Nadeau vanishing. So I better work out what the linear equivalence class or numerical equivalence class of C is. So C is going to be Q linear equivalent. Okay, so by definition, it's 1 minus epsilon G plus F. So that works out to be 1 minus epsilon dm minus 1 plus h plus 1 minus epsilon delta vm plus lm minus 1 k epsilon d. There's nothing magical going on. G, there's a 1 minus epsilon G, but G is dm minus 1 plus h, dm minus 1 plus h. That's right there. And then there's the F. Well, F was a bit more complicated, right? Because F was 1 minus epsilon dm plus ln minus 1 k epsilon d. ln minus 1 k epsilon d, 1 minus epsilon delta bm. So I just rewrote that stuff. Okay. So we're almost there. So if I want to apply the proposition, I need some n minus d to be ample. Okay? So I'm going to preemptively compute some ample divisor and then show you that it's n minus d. So my ample divisor will be epsilon d rm minus 1 plus h plus delta bm plus pm. So this is ample.
Is D or D?
Sorry?
Is that D or D?
Is that d?
Or D here?
Yes. It's the same one.
Same D.
Yes. It's the remainder one. Right? There are lots of d. There's one for every m.
No. Oh, so you said you were going to apply. Oh, so you're going to apply the proposition.
Which one is the d? Probably C. Something that looks like C. I haven't. The next line I'm going to show you.
Okay.
I'm going to reveal. This is all the preparation. All my soldiers are ready to go to battle. But let's just check this. This is again a triviality because P is Neff. So I just have to check that this is ample. This guy here is very ample because this is in the range between 0 and k minus 1, and h is sufficiently ample. Delta is sufficiently small, so this thing is still ample. And epsilon times ample is ample. So this is a triviality check. Okay, so now we are ready. We just need to check the hypothesis of those two things that were done. So I'm going to look at dm plus h. So what's the m plus h? Presumably that's the sections I want to extend, right? I'm trying to extend the section from dm plus h restricted to S. So, so this is of the form kx plus s plus dm minus 1 plus bm plus pm plus h. So this is just using the definition of dm, right? The difference between dm and dm minus 1 is going to be one copy of kx plus s, and you figure out the other terms. So this is exactly what you get. And I may have written it explicitly somewhere, but I don't see it explicitly. But it's easy to check that this is what.
You did right there.
Okay, great.
Yeah. Everything is plus.
Yes. It's hard to see that this is a plus, huh? Indeed, everything is plus. Okay. So now this is kx plus s. It's going to be a mess because I want to have c appear in there, right? So I'm looking for what's c? 1 minus epsilon d. I'm looking for this, isolate that mass in there. So I should have a 1 minus epsilon dm minus 1 plus l m minus 1 k epsilon kx plus delta plus epsilon drm minus 1 plus bm plus pm plus h. So let's think about it. bm plus pm plus h is right here. Kx plus s. Okay, kx plus s is right there. And dm minus 1. Right. So here's 1 minus epsilon of them. So I have epsilon dm minus 1 left to account for. Everything in here, you can factor out an epsilon. So what I need to know is that dm minus 1 is ln minus 1k kx plus delta plus dr sub m minus 1. Yes, you found it somewhere there and I can't find it. By the definition of
the RM and the LM.
I feel so stupid that I cannot. Help me out, Kenji. You said it's by the definition.
Yes.
By this line here?
No. You define this
I think that what one has to do here is the following. One has to get it from this definition here. So the dm is the sum from 1 to m. You split it into two parts, that sum. The first r sub m minus 1 terms and everything else.
I take it back, yes.
Yeah. So you split it in two parts. The first r sub m minus 1, which clearly gives you d r sub m minus 1. The rest is divisible by k, so automatically gives you an integral divisor, which is k times km kx plus delta. So that's it.
So there is something.
Yeah. So you have to. So really, the thing that follows from is the definition of Lm, Rm, and splitting the sum into two terms. So there is a epsilon of work that goes into checking that. Okay, so now this is Q equivalent to kx plus s plus a plus 1 minus epsilon dm minus 1 plus lm minus 1 k epsilon d plus 1 minus epsilon delta bm plus 1 minus epsilon.
Chris, I'm sorry.
Yes.
In the second line, is that epsilon k?
Second line of which? This one here?
Yeah, and epsilon, and there's a k there?
Here?
No. The next term. Epsilon d r m minus 1. Is there a k in between?
Here?
No. There. Second line. Yes, and the next right goes slightly. Yeah, is that?
That's an epsilon.
There's a k?
No. There is no k. I don't believe. Yeah, and the reason is exactly what I just explained. So when you look at this summation here, you split it into two parts. One part has Rm minus 1 terms, and that is what is giving you drm minus 1. The other part has Lm minus 1 times k terms. The k, right, so it should be, there it is, Lm minus 1k terms. So right, I'm just using the fact that I can write Lm minus 1, here we go, m minus 1 is Lm minus 1k plus Rm minus 1. That's my Lm minus 1k here, and that's my Rm minus 1. Right, so when I'm computing dm minus 1, this is a sum I equals 1 to m minus 1 of something, right? So it's going to be the sum I equals 1 to Rm minus 1 plus the sum from Rm to m minus 1. So Rm minus 1 plus 1. That's it. Okay? And this guy here is precisely drm minus 1. And this guy here is going to be k Lm minus 1 times kx plus delta. So that's where that extra k is coming from. It's not really a k there, right? Because this is just an approximation of the number Rm minus 1. Right? Sort of, it's the biggest number divisible by k next to it.
But how about the second term when you're summing up? Is it always going to be?
Is it always going to be integral? Yes.
I have to think about it.
Because k clears the denominators of anything inside.
Oh. I have to think about it.
Yeah. Yeah, there's just so many terms, it's hard to keep track. I'm surprised that I'm managing to. Okay, so for example, 1 minus epsilon dm minus 1, I just repeated it. Lm So D was linear equivalent to kx plus delta, so I did nothing to this term. Something more interesting seems to be going on there. So the non-interesting part, this guy are just here, and this guy here is here. So the interesting part is this A, 1 minus epsilon Bm. Okay, so there's this minus epsilon delta Bm, and then there's this 1 minus epsilon H, or an epsilon H. And if you look at the definition of A, it's all of those interesting parts with a factor of epsilon. So that's how they match up. Okay, so the next step you're going to like, because this is Q linear equivalent to Kx plus S plus A plus C. Yeah, all of a sudden, right? I mean, so what was C? C was all of that mess, right? C is 1 minus epsilon dm minus 1 H, 1 minus epsilon delta, Bm, Lm minus 1, Lm minus 1 K epsilon D. There's an S, there's an A. So if I haven't forgotten anything important, but I don't think I have, this matches up. Now you see, so in order to apply the extension result, I need that n. So if this is my n, well, this is my n really. So n minus s and c minus kx plus s plus c is an ample divisor. So the difference is ample. So this is telling you that sections.
Wait.
Yeah.
N is dm plus h.
Yeah, this is going to be n.
This is your n. And what is d?
D is c, because unluckily I've used D for a million other things here.
But the d is c?
Yes.
So n minus c is kx plus s plus n.
But kx plus n there. So that's that difference of kx. And there's actually a small typo in that formula that we discussed last time.
No. You said n minus d must be ample, but I don't.
Okay, so this is n plus kx.
Oh, I see.
And now
I see.
I'm expecting you to say, oh, but you're off by s.
Yeah.
Yeah, actually I have a typo in the previous one, right?
Oh.
Because no, I did it right. So in the next line, I have a plus s appearing. So I don't have a typo there.
You're right.
Yeah. Okay, so that proposition tells us that sections of H0 dm plus h tensor the ideal of C restricted to S extend. Okay, so now all I have to do is, I asked the question, is what was I trying to extend? It was some multiple of sigma plus some u probably. Lm sigma plus um. So the question I'm really hoping the answer is yes, otherwise it's all wasted. Is this guy here in here? Well, I've already checked that it's in there because I have Lm sigma plus um plus a KLT thing is greater or equal to C restricted to S, and that's precisely the lemma. So that's true, and that concludes this proof.
Oh, wait, proof of the claim.
Right, so then by induction, that claim is true. And whenever this claim is stronger than the theorem, because the theorem coincides with this claim whenever m is divisible by k. So that concludes the proof. So I don't know what to take away. The proof is completely trivial, but coming up with the right statement and fiddling with the divisors. I mean, I can't tell you how many afternoons I invested in trying to get the right divisors, right? You sort of, you start with, but I mean, Kenji, maybe you know, I imagine that when somebody proved the base point free theorem, it was a similar experience. They probably had to play, it was, you know, you're avoiding this induction, but you still have to fiddle around with the right divisors. Okay, okay, so I have not done the proofs of every step in the proof of the existence of flips, but this is probably the hardest part. So in some sense, I did the hardest technical part of the proof. Okay, so now...
are you going to show us how you get rid of
H?
H.
Yeah, that's the next thing. But since I've used up exactly an hour, I thought maybe a 5-minute break would be a good moment to take a 5-minute break. And then I'm not going to do, there'll be another statement similar to that without the H. I won't do the whole proof. I'll show you the key part. So I'll put a couple of divisors equal to 0, so I don't have to do blackboards and blackboards. I can get it done in one blackboard. But you can still get the main idea. So, you know, you suffered through this one, but the next one will be more pleasant. So let's take a 5-minute break. To do is try and write a version of that gets rid of the H. Well, maybe I'll need a little extra hypothesis to get rid of the H. So let me do that. But now the statement is getting very close to what you need for the existence of Kyoto. So now I'm not going to talk about a smooth pair. I'm going to move to a PLT pair. Well, maybe not. Maybe let's keep it log smooth. So by saying PLT, it just means that S is irreducible, no common components with D, the round down of D is 0, and it's log smooth. A is some ample divisor. Delta is S plus A plus B. Is that what it was before? Well, okay. There's an A. The P became an ample divisor, but it's similar. C, no relation to the previous C, is something effective such that SC is canonical. I'm going to assume that M is an integer such that MA, MB, and MC are integral divisors. Well, come here, since everything's good. And I'm going to pick some Q sufficiently big such that QA is very ample. S is not contained in the base locus of QM KX plus delta plus A over M. So essentially I'm thinking that S is not contained in the stable base locus of this linear series. And C is going to be less or equal to B restricted to S minus B restricted to S wedge 1 over QM fix QM KX plus delta plus A over M. So S.
C is a divisor on S.
C is a divisor on S. So yeah. So this is, that's why I wrote archetype here, not in some divisor group. So this is on S. These two guys, I think, are on X, right? Yeah. Okay, so I'm assuming that. So remember last time I sort of tried to explain why you're supposed to throw away common components between B and the fixed locus, because regardless, something that is in the restricted linear series has to vanish along this fixed locus. So preemptively throwing it away, and then
so fix parenthesis, right?
Okay, so you want a parenthesis.
No, not there.
Not there. Where do you want the parenthesis?
Fix of the Q and X plus delta A over.
Because you're afraid that otherwise the symbol could mean take the fix and then restrict it to X.
Yeah.
But it's the same thing. This is the restricted linear series. So I take divisors on the ambient variety, restrict them to S. Oh, it's not exactly the same thing, right? Because it could have, okay, so this linear series, its base locus could be a codimension 1 point on S, which is codimension 2 on the ambient variety, so it would not be measured by that. Okay, so well, there's no harm in putting an extra.
No, too many.
Two. Okay, I have a tough task now.
Sorry.
I could have sort of, if I said sort of a stable base locus with multiplicity, I could have avoided that action.
And there's one more question.
Sure.
When you write fix, this is the divisors in the fixed locus. Is that what?
Counted with multiplicity.
Counted with multiplicity.
Yes.
That's your notation.
Yes.
Okay.
Right, because otherwise, here I'm taking the divisor in common between this and that. Otherwise, I would just be throwing away the whole component. No, I just want to, essentially, I want to look at B, and I want to say, well, if something in B is contained in the stable base locus, it shouldn't really be that. So let's subtract off.
So when you write FIX, you only care about the divisor part of the fix.
Yes.
Okay.
That's all we care about. Yeah. And it's a bit surprising that you can get away with that. But somehow the canonical condition is helping you. Like canonical is saying that there's no higher interesting centers, higher dimension interesting centers. Okay, then, here we go. M, K, S plus A restricted to S plus C plus M, B restricted to S minus C is contained in M, Kx plus delta sub S. Okay, so what I'm saying is I cannot just extend the whole linear series, but I can extend those sections which vanish along this guy. Right? So essentially, I guess this should be my theta, the thing that I'm thinking about theta. Now, have I done something bad? Not at all, because when you're looking at the restricted algebra, as I tried to explain, the restricted algebra has to vanish along these things, right? It has to vanish along something, it has to vanish along the fixed linear locus of this. But, okay, so let me emphasize that. The fixed locus of, oh my gosh, I need to put it back. Okay, this is fine. M, Kx plus delta sub S is contained in, well, maybe I should put, it's contained, is greater or equal to Q, to 1 over Q, the fixed locus of the thing I have up there, Q, M, Kx plus delta sub S. This is just because if I take this linear series times itself Q times, I land in here, so this fixed locus times is less or equal to Q times this fixed locus. And this is greater or equal to 1 over Q, the guy I have up there. Right? Because if I add a little bit of an ample divisor, the fixed, I have more sections, and so the fixed locus will be even smaller. Right? So if I'm trying to apply this to something about the restricted linear series, I know that every section in the restricted linear series has to vanish along this divisor here. Right? It has to vanish along this fixed locus, because that's bigger than this, smaller than this, right? And in fact, I have room to spare. Any divisor along which it vanishes this inequality will be strict because I have this ample. So for Q sufficiently big, the ample will kill off a bit of that component. Right? So this, I have some room to spare. Now I'll try to say a bit later. I'm going to use that room to spare when I prove that theta is rational. Okay, so that's why this is sort of a robust statement, a statement that's going to be useful. So when you try and prove it, it's similar to the proof of the previous result, but I'm just going to emphasize the key step, the key difference. So if you know about multiplier ideal sheaves, this is very much reminiscent of the fact that multiplier ideal sheaves are integrally closed. Right? What does integral closedness mean? It means that you multiply your function, you take powers of a function multiplied by a fixed text function belonging to powers of the ideal, then the original function belongs to the integral closure of that ideal. It's essentially the definition of integral closure. Well, here we have that multiples of the divisor times a fixed, multiples of our function times a fixed function belong to some linear series, and then I'm sort of leveraging that. So it's very simple. Okay, so
but this C may depend on Q. So you have not found theta, which is independent of.
No, I need to then settle my theta, but that's going to be pretty easy to do.
But
yeah.
this theta depends on Q, yes?
Right, so essentially what you're going to do is you're going to define this guy here to be theta sub Q or something.
Yeah.
And then you take the limit of those. Now the limit will be some horrible real divisor, so then you have to do different approximation. That will be your C. Something like that. And this is not, this is the thing that this is yes, B should just minus theta. That theta Q. That's what it is. I'll define it later. Let me show you the key step in proving this so that you believe that something like that can be done. So let's assume, let's make some simplifying assumption that C is equal to B restricted to S. So I don't, this is just, makes my life easier so I don't have to write B restricted to S minus C everywhere pretty much. Here I have my section sigma in M KS plus
So you don't subtract nothing?
Right, so assume that you're lucky and the fixed locus has nothing in common with B restricted to S.
I see.
Now, you take the section that you want to extend, right? I think that's the thing that would. So now, this is 0. So we're supposed to extend any section in here. C is equal to B restricted to S. We want to extend that section. Okay, so by previous theorem, we have that L sigma plus U does extend. Is an L times M K X plus S plus A plus B plus H S for every L greater than 0 and some H fixed sufficiently ample divisor. So this H does not depend on L. That is key. Okay, so in other words, we have this extends, so you have a divisor, let's say GL, in that linear series, which when I restrict it to S, I get this divisor. Okay? So now, I'm going to look at the following. M, K, X plus S. I erased the proposition, but I'm trying to apply the proposition. Minus K, X plus S plus GS. Well, let's put the coefficient in front. M minus 1 over L M GS plus B. Okay, so this is the thing I'm going to take the multiplier ideal sheet for.
What's GS?
GS? Oh, GL.
Can you rewrite G? That doesn't look like Sorry, Chris, you can punch me.
That's the best I can do. Okay, so this is numerically equivalent, I claim, to A plus, hopefully I did my computation right, because I'm simplifying a proof. So. Okay, so let's see, did I get this right? So m minus 1 over ln GL, what's that linear equivalent to? Well, the ln will cancel with this, it's linear equivalent to m minus 1 kx plus s plus a plus b plus a. So m minus 1 kx plus s and another kx plus s, that's n copies of kx plus s. So that's taken care of. Then there's m minus 1 copies of b and another copy of b. That's taken care of. I did not put a copy of a, so I have one a left over. There it is. And then, how about the h's? There are no h's on this side. There's an h, there's an lmh in here, so I get, hopefully, I put the wrong coefficient, but it's still going to be okay. So it's m minus 1. Oh no, I put the correct coefficient. Yeah, m minus 1 over ln copies of h. H has no coefficient here. For some, I was worried that there was an ln but there isn't. Okay. Okay, so now, for L sufficiently big, this guy here is ample. So that tells you that the cohomology, higher cohomology of m kx plus s plus a plus b tensor the ideal of m minus 1 over lm gl plus b is equal to 0.
A is ample, H is ample, yes?
Yeah, and there's a minus here, but it doesn't matter.
Oh.
It's still ample.
It doesn't matter.
I mean, otherwise it's,
well, otherwise,
there's
yes.
no point in
L,
saying
yeah. Okay.
Yeah. So that's ample. So I'm supposed to say minus s here. There's the s there. Okay, so this h1 is 0. Higher cohomology, this is just my NATO vanishing, right? Because this is, in the old notation, this was your n plus kx plus s. So now, if I get rid of the kx plus s, then this is that divisor that I have to put. This is what, in the old notation, was the divisor d. So I have to check that n minus d is ample, which I just checked. Then higher cohomology of kx plus s plus n minus d is, of kx plus n minus d is 0. That's why there's a minus s there. And so that is telling me that I have surjectivity. Let me not write what this group is, but the sections that lift are the sections in m, k, x plus s plus a plus b, restricted to s, tensor the ideal of this messy divisor m minus 1 over Lm. Okay, this divisor restricted, let me just write, restricted to S. What is GL restricted to S? It is L sigma plus U plus B restricted to S. Okay? Now, B restricted to all I need to do is I need to check that sigma vanishes along this ideal. So I need to check that this quantity is less or equal to sigma plus KLT. So let's look at that quantity. That quantity is, I'll just rewrite it. It's less or equal to, okay, Lm n minus 1, that's less or equal to sigma, plus B restricted to S, plus m minus 1 over L m u. Okay, so let's think about it. I want this to be KLT. B restricted to S is KLT. For L sufficiently big, this is a fixed U. So for L sufficiently big, this is a sufficiently small perturbation of a KLT divisor, so it's still KLT.
That's plus, yes?
Yes, that's definitely plus. Plus, so this is KLT for every L sufficiently big. Because this quantity here is going to 0, and this is a fixed divisor, so if you have a KLT divisor plus an arbitrary small divisor, that's again KLT. KLT is an open condition.
And this implies what?
So this implies that, so this divisor is less or equal to sigma plus KLT. The lemma, remember the first lemma I did today, says that then sigma automatically vanishes along the ideal of this divisor. So sigma automatically vanishes along this ideal. So sigma is in this group, so sigma extends. That's what I wanted to prove. Right? So the punchline in these extension theorems is always two things. One, some H1 vanishes, so you have surjectivity. And two, the section you want to extend lies in the ideal. Actually lies in the group that you can extend. This, algebraically is pretty easy to do. Now that you've seen it once, it's just this computation here. When you do it analytically, it's much more complicated, but you can get stronger results. So if we did not have a little bit of ampleness, we wouldn't be able to do this. That's why Sue's methods work for pre-genera for intermediate cardinal dimension as well, not just for general. Okay. Okay, so there's two more things I need to do before we're done, and I might actually be able to do it, much to my surprise. One is I should actually give the definition of theta q's and try and explain, at least give some intuition why the limit is actually a rational divisor. And two, I should show why for a PLT flip we can assume all of these extra conditions. That you can write it as S plus ample plus B, and you can assume that this C is canonical, all of these kind of things. Right? There's a few extra technical conditions that are not in the definition of PL flip, but they're easy to arrange. Okay, so this next statement has, if I can find it, has the definition. Yes, here we go. So now, x is q factorial. I'll stop pretending that x is projective, but I have a projective morphism to a defined variety. I'm going to still have an ample divisor.
Sorry, Chris.
Yes.
Where did we use the SC canonical convention in your proof on the blackboard?
So I know. Yes.
Where did you use it?
So I know morally what's really going on is you are sort of trying to subtract off common components between the fixed locus and B. If you want this to be robust from a birational point of view, you would like this condition to be verified on higher models. If it's canonical, there are no components of this that live on higher models. Now,
we didn't see it because you pretended to see it.
yes.
Okay.
I think that's what's going on. Okay, so I have this projective morphism for the fine variety, I have this ample divisor, I have a PLP pair. It's no longer log smooth, okay? PLP. And then I'm going to assume that S, B sub S, so this is a gadget induced by a junction, right? So Kx plus S plus B restricted to S is Ks plus Bs. I'm going to assume that this is canonical. And I'm going to assume that the stable base locus of Kx plus S plus B plus A does not contain S. And then let me let Fm be the fixed part of M.
Does not contain it.
Thank you. Kx plus S plus B plus A restricted to S. And I'm going to divide it by M. Okay, so this is our friend from over there. And then I'm going to take the limit of these guys. So F will be the limit. I'm going to say the limit of Fm factorial because otherwise it's not completely obvious that you can compare them. You cannot compare F2 and F3, but you can certainly compare F2 with its F6 and F3 with F6. So let's just take the limit over Fm factorial. Just make, you don't even have to think that way. Then we have theta is going to be B sub S minus B sub S with F. So the claim, so a priori, this is an R divisor on S. And my claim is that this is a Q divisor. It's a Q divisor, and if K is an integer such that Kx plus S plus B plus A and Ks plus theta plus A are Cartier, then Rs K Kx plus S plus B plus A is equal to R K Ks plus theta plus A. Everything is looking good, right? Okay, so this is almost exactly what I want for a PLP flip. The only difference is, why is this extra A here? Yeah. It will be easy to put there. We'll do it in a second. And why is it canonical? Maybe I'll do the reduction. I'll tell you why this implies the theorem directly. But it's almost exactly what you were expecting, right?
But the A is there.
Yeah, well, okay. So let me show you why this implies PL flips, and then let me say a few words about how to prove this. Okay, so I'm deliberately doing the easy thing first. So what does a PL flip look like? We have F from X to S. This is a small birational contraction. I can assume that S is affine. Ooh, I certainly don't want to call it S. Let me call it Z maybe. Small birational. We can assume that Z is affine. We have X, S plus B is PLT. So already you're saying, oh, you're a bit off. You're supposed to have B plus A, and you only have S plus B. Okay, this is PLT. What else do we have? We have minus KX plus B is F ample. We also have that minus S is F ample. We probably don't need to use it at this point. We already used it to know that it was enough to show that the restricted algebra is finally generated. Getting there.
Did we use that?
Yeah, we used that in proving Shogor's result that finite generation of the restricted algebra implies finite generation of the whole algebra.
Where did we use minus S example?
We used it because subtracting S shifts the degree down by 1 instead of shifting it up. It was just in the mechanics of showing that the kernel is an ideal. Otherwise, you get the kernel is something sort of something not contained in the ring itself.
I missed that.
So we did use it there. At some point, I wrote minus A kx plus S plus B is linear equivalent to BS.
Yes.
You remember that? So yeah, that's what I was using. It would be a positive. Okay, so getting back to the situation. So this is my PO flip. It looks a bit like that, but not really. So I'm going to massage it a bit until it looks exactly the same. So I'm going to pick, so I'm assuming that Z is affine. So any divisor on X has lots of sections. The only base locus of a linear series on X is just the exceptional set for this map. So now I'm going to pick S prime, linear equivalent to S, which has no common component. We've done this before. And I'm going to pick B, which is going to be, well, B I have. It's big, so in particular it's Q linear equivalent to, let's say, A plus C, where C is effective and A is ample. Right? I mean, this is a small map over a affine variety, so any divisor is big. So now I'm going to let A prime be epsilon times the sample divisor, and B prime is going to be 1 minus epsilon B plus epsilon C. And then, obviously, Kx plus S plus B is Q linear equivalent to Kx plus S plus A prime plus B prime, where A prime is ample, B prime is effective. Now you may say, oh, wait a second. When you chose this C, it could happen that C has multiplicity along S, right? So in that case, you would destroy the PLT property, right? Because the key thing in the PLT property is that the multiplicity of B along S is 0, right? So what do you do if C has multiplicity along
Wait,
S?
say again? PLT is just that there is no, S is the only
thing of coefficient 1.
Yes.
If you add, if C vanishes along S, then right now inside my B I have a little bit of S, so now the coefficient of S will be bigger than 1. So I really need to do this trick. I really need to know that C has no component in common with S. I need to guarantee that. But that's super easy because I just told you that S is linear equivalent to something else which is not S. So suppose that C was alpha S plus a divisor gamma, then it will be Q linear equivalent to alpha S prime plus gamma. Oh, now it has no component of S in it. So, so that was easy.
So by this trick, you can also assume that X is not in the BS of the K.
I can also assume that what?
The X is not contained in the BX of the KX plus X plus B plus A.
Ah, yes.
So by this trick.
But I want S to be contained I mean, I want it here, right? Ah, it's not contained in the B. Yes, yes. So
But
now
that was part of it. Definitely.
that's part of the assumption, yes. Yeah, so more to the point is when I do these perturbations, I never run into that problem. So okay, so now I'm still slightly unhappy because,
Why?
well, it's not canonical, right? But I can blow it up and make it canonical. I can take a terminalization of S, essentially. So here's the picture that you have in mind. If this is your S, and on S you have two components of B that maybe have coefficients like 2/3 and 2/3, then this is not canonical, because if you blow up this point, it will appear with multiplicity 1/3. So blow it up. And then blow it up, well, in that case, it'll be, blow it up as many times as you need to make it canonical. Yes?
Then you are changing the situation. S was sitting in X. What do you mean by blowing it up?
Write it down. Okay, so now,
What do you think with that?
He's gonna write it down.
Write it down. Oh, sorry about that.
yeah, so I'm preparing, I'm telling you what I'm going to do, and now I'll do it.
Okay.
So I write ky plus gamma is the pullback of kx plus s plus b prime plus a prime plus e, where as usual e and gamma have nothing in common and they're two effective divisors. And now this guy here is PLT, right? Because whenever you take a log resolution on a PLT thing, you still have a PLT thing. And we can assume, so let's let T be the strict transform of S. We can assume that when I do, when I consider T and gamma minus T restricted to T is canonical, is terminal. I want to assume that it's terminal. Okay? Then you say, oh, great, you've done it, but then you say, oh, wait a second, I want that gamma contains an ample divisor, right? So this gamma is the S plus B plus A. It has to contain an ample divisor. So why is that? So you see, what I'm going to do is, let's pick.
Why is it terminal?
Why is it terminal? Because you take a
Or you need sufficiently high blow up?
Yes, a sufficiently high blow up, I can guarantee that it will be terminal on S.
So it's a part of the condition on G.
Yes, exactly.
Okay.
Of course, if I take G the identity,
I know.
that's what's going to happen.
So what you're saying is pick G such that.
Exactly.
Okay.
Such that I make. And now I'm going to pick F, an effective divisor, such that minus F is G ample, and F is exceptional. And let me add epsilon F to both sides here. Then you see gamma will be greater or equal to the pullback of A prime. Okay, I don't want to add it. Yes. Gamma will be, so what I'm going to do to gamma is I'm going to add epsilon F and subtract epsilon F. Because you see the point here is that the pullback of A prime minus epsilon F is...
I'm sorry, Chris, I cannot read.
Yes, I will...
Gamma is what?
Okay, so gamma is just gamma. So now I'm going to perturb gamma. Well, I'm not going to perturb it. I'm just going to
Plus epsilon.
rewrite it.
Sorry, I cannot read. Okay.
I'm rewriting gamma as gamma plus epsilon, this effect, exceptional divisor, minus epsilon, the exceptional divisor. Did nothing, right? But now you see gamma contains a pullback of A prime. If A prime is a general ample divisor, then the strict transform of the pullback of A prime are the same. So gamma will contain the pullback of A prime. Minus epsilon f, that's an equivalent to an ample divisor A. Let's call it A on Y, an ample divisor. Okay? So what I'm doing is I'm replacing gamma by a Q-linear equivalent divisor to gamma, which is gamma is Q-linear equivalent to gamma prime minus epsilon f minus g upper star of A prime plus A y gamma prime is, I take gamma, I subtract epsilon f, add epsilon f. Okay, here we go. Okay, so I'm going to replace gamma by the following divisor, which is Q-linear equivalent to gamma anyhow, which is what? I add epsilon f, I throw away the strict transform of A prime, and I put in this AY, which is ample. So replacing gamma prime by an appropriate Q-linear equivalent divisor, I can assume that it contains an ample divisor. And this epsilon f doesn't harm me, because if that was terminal, this plus epsilon f restricted to t is also terminal, because terminal is an open condition. So this is sort of a standard manipulation which shows me that starting from the PLT situation, I can reduce myself to this more special situation. In fact, I can even assume that x is smooth, right? That's a log resolution. So I can assume that x is smooth, and that makes my life easier, I guess. And the divisor in question, I guess, has simple normal crossing. I can assume that too. So all I'm trying to say is that there's some standard reduction from the PLT flip case to this situation. And now, in the last 5 minutes, try to reduce, tell you why this theorem should imply that theorem.
Yes.
So there's two parts. One part is to show that theta is rational, and the second part is to show that all the sections extend.
Yeah.
Okay, let's assume first that theta is rational, right? Okay. So what we're trying to show is that we have this implication.
That's okay, but theta is smaller.
Sorry?
C is smaller, no? So it extends. No? If it's rational.
We got a trick. C is smaller than this minus that.
Oh.
But this is actually, I told you that this is strictly smaller than the fixed part.
Oh.
So
that may not be satisfied.
No, it's easier for this to be satisfied. So C does not have to be, it does not have to be smaller than B. You don't actually have to subtract off the whole fixed locus. You have to subtract off like 1 minus epsilon times the fixed locus. So actually, this theorem is much more powerful than it looks. You can extend more sections than you think. Okay. This factor here allows you to fudge things a bit, and that's how you know a priori that the base locus on the ambient variety restricted to S is the same as the base locus on S.
But,
Right.
but this middle one is smaller than theta, no?
No, that's what I'm trying. This thing here is not smaller than theta.
Why
Okay.
not?
Okay. So that's kind of the crux of the argument. So let me go in the order I was trying to go. So let me start by saying, if we know that theta is rational,
Yeah.
then we can extend the sections, right?
Yeah.
So
But my problem is the middle one might be smaller than theta.
okay. So it's not.
It's not.
Okay. So let's to get some feeling. Suppose theta is rational.
Yes.
So let's suppose that k theta is an honest, we can clear the denominator, is an honest divisor on S. Okay, so I was looking to see if I explain this in my notes. Okay. Then A plus theta, hopefully this helps, minus B restricted to S minus B restricted to S minus 1 over Q M F. This is essentially what you're asking about, so is M. Okay, so let's think about what I just wrote. Example for every Q sufficiently big. Okay, so how do I get theta? I get theta by yes, by this recipe, right? I think I wrote it down somewhere. Yeah, I do bs, and I subtract off bs minus f, where f is the limit of these fixed parts, these fm. So this fm cubed is the same as that. Fm is the fixed part of kx plus s plus b plus a. And okay, so the limit of divisors like this is theta. So for any ample, so eventually this difference is small. So any ample, and it's supported on finitely many on the support of B, so it's every coefficient is small and it's only finitely many divisors. So eventually this guy becomes ample. I'm not saying anything deep. Okay, so then that should be enough to say that the sections have to extend. So what I write down, and then I hopefully can justify it, n kx plus s plus, I guess, maybe I want to say k, kx plus s plus b plus a, should be the same as m ks plus theta plus a plus m b s.
So you're actually trying to show for sufficiently large Q, the coefficient of the right-hand side becomes the same as theta, the last term. Is that what you're trying to show?
Well, okay, so now I've assumed that it's rational. So what I'm trying to show is that this theorem is going to apply to give me that these sections, the sections of this form extend. Right? That's what I'm supposed to do.
So is it showing that the theta, A plus theta, is actually the coefficient of theta of some component in theta, and B restricted to S minus B restricted to S wedge 1 over QM, FQM, they have the same coefficient if Q is sufficiently large?
Yeah.
Is that what you're...
Yes. So, okay, so let's think if this follows from that. Hopefully I didn't mess it up. So what am I supposed to check? What I need is that C, I need to subtract off, is it more or less than something? So yes, so here, this says that I can extend all the sections as long as I subtracted off at least this much. So what I have to check is that I subtracted off possibly more than this. Okay? But that's what I just erased here, because what I subtracted off was the stuff in common with the base locus of this linear series. This is my delta, right? Whereas here, I'm only asking that you subtract off stuff in common with this linear series where I've got an extra ample divisor in the picture. So this guy here is a milder condition. I'm asking you to subtract off less stuff. So this is fine. That satisfies that problem. So now, rationality is a bit more involved. You have to use this little flexibility. So what the rationality is telling you is that in fact we had a bit of room to spare in the argument that we just did. So suppose that theta is a real divisor. Then what you look at is some other divisor C, which is a Q divisor, which is sufficiently close to theta so that it still satisfies the inequalities that you need to extend sections. Then you know that you can extend sections, so you know that the stable base locus of this linear series is exactly the same as the stable base locus of the corresponding linear series here. But this one is rational, because you have a rational divisor and you're in dimension 1 less, so you can apply finite generation of the pluricanonical ring. So the thing that you're afraid is irrational and gives you an irrational theta divisor, the stable base locus of this linear series, you can now compute to be rational. So to...
Oh, wait, I don't understand the last part. So what's that? Okay, so I take C, which is close to theta.
Right.
Yeah.
Okay, so we know, so instead of this statement, you'll have it with MKS plus psi plus A. So if I look at this base locus, this is, well, okay, so.
Are you taking C from low, from smaller or upper?
Okay, you're asking too many questions. Because, no. The point is, if you want to get it right, you have to ask the question, is it from upper or from lower? Off the top of my head, I'll get confused if it's from upper or from lower, right? And in order to get it right, you have to use the Fontana approximation. Because in order to check that everything, the difference is still ample, etc., you need difference between these two divisors to be small with respect to the coefficients. So that's done with respect to that Fontana approximation. I think you pick a coefficient of theta that's irrational, you pick C to be just slightly smaller, and then it allows you to compare the stable base loci. Maybe it's slightly bigger. So, but the punchline is that if you look at the limit of fix of this divided by m, this is a Q divisor. By finite generation on S, which you know by induction of dimension. By the fact that you can extend section, that tells you that all the coefficients in question are rational here, but you had some coefficient that was irrational. You're assuming that theta was irrational, and that's a contradiction. because you're just saying that some component with an irrational coefficient which becomes rational when you restrict it to S. Okay, so I'm being quite sketchy about this part. It's about 3 pages in the notes to do it right. And you have to say the words Diophantine approximation, and you have to consider the smallest rational fine vector space spanned by theta. So it is a little bit fiddly. But the main idea is just, once you can lift sections with this extra degree of freedom of A over M, you can really compare the base loci on the ambient variety and on the divisor. On the divisor, they're rational, so they have to be rational on the ambient variety. That's, yeah, so sorry I didn't get to do the details of that part, and I stopped here. I'm a couple of minutes over time, sorry.
Thank you.